So I'm going to give a little bit of an overview and set some tone for the rest of the day, or at least that was what I was asked to do. I'm not sure how successful it would be. Talking about science, reproducibility, credibility, and excellence. Science has clearly been a success story. There's no doubt about that. I think that science has been the best thing that has happened to Homo sapiens sapiens, and in terms of the impact it has had in our lives. It's beyond any question that it has been tremendous. We have many hallmarks of that success. We have 180 million documents that have been published. We have more than 9,000 authors who publish a paper every 5 days. We analyzed all 20 million authors who have published a single scientific paper in Nature a few weeks ago. Some have amazing productivity. We have lots of success stories in terms of major awards, more than 700 Nobel Prizes given in medicine or physics, chemistry, and economics. We have more than $2 trillion invested in research and development around the world every year, with hopefully still some growth, but also some tension about even these funds not being sufficient to really sustain the explosively growing enterprise of science. At the same time, we have some signals that some of that success is just too much. And maybe not all of that is genuine and true. A couple of years ago, we analyzed the entire PubMed worth of data, and from 1990 until 2015, we're talking about 15 million papers. Whenever there was a p-value, 96% of the time, these papers, in the abstract and also in the full text, in about 1 million full text articles that we could download, they had statistically significant results. And practically, they almost always said that this is novel, exciting, important, worthwhile. So significant discovery, in a way, has become a boring nuisance. You know, we just have so much of it that we need to find ways to pick really what of that huge enterprise can really translate to something that can move forward, to lead to genuinely important insights, and also, in fields like medicine, do some good. You know, save lives, improve quality of life. And the same applies also to other applied fields. So the good thing is that we have more negative results over time. So that 96% is for the overall period, but actually it has decreased from 98% to 95%. So maybe there's a little bit of more tolerance for some negative results, and more people recognize that these negative results sometimes may be as informative or even more informative compared to positive results. We also recognize that translation, which means taking a basic science discovery all the way to the clinic and to the community and making it work, takes a very long time. On average, it takes about 25 years. In some cases, it has taken more than 100 years. There's a few fast and furious success stories, like, for example, HIV disease. I felt extremely privileged to live the era when triple therapy was proposed, well, discovered first. You know, you had these antiretrovirals discovered like protease inhibitors, and within 4 years from discovering a protease inhibitor, reaching all the way to having a randomized clinical trial, ACTG 320, where I was involved, where we showed that you can dramatically decrease mortality in these people. And you saw a disease transformed from something that was killing every single patient that I was seeing before that to a condition that you can live pretty much a normal life with normal life expectancy. But on average, this is not the typical story. On average, we're talking about long delays, and we're also talking about situations where even when you reach the point of having an extremely influential, highly cited clinical trial, like the ones that I show you here, which are the most highly cited trials in the history of clinical medicine. These are the red points. Even at that point, you have a 40% risk of an even larger, better controlled study to refute that major seeming discovery. So there's a lot of angst about reproducibility. how many of our results can we trust? How many of our results can we move forward? Across all 22 major fields of science, there is an exponential growth in the use of terms like reproducibility of results. But each one of us may mean different things when we're talking or thinking about reproducibility. There's basically three major types of reproducibility. There's reproducibility of results, of methods, of results, and of inferences. Reproducibility of methods means that you have some software, some script, and some data, and if you mix them together, you expect to get the same result. It may not be always exactly the same. So for example, if some Monte Carlo simulation is involved, it's possible that maybe some third decimal, maybe second decimal may not be exactly the same, but it should be pretty much the same. If it's not the same, then we're in trouble. Do we know whether it is the same? Most of the time, until recently, we could not even tell whether it is the same, because it was very, very uncommon that both the data, raw data, and the software and the script would be in place for anyone to check. Now, we would have to take our colleagues' word in good faith that here's my scientific paper. It's not really a scientific paper. It's an advertisement of some scientific paper and of some work that I did. And please trust me, I did all of that. Yes, the data is somewhere. I don't know where. And yes, the software was working. Oh, come on, you want to waste your time trying it out? And the script, yeah, the statisticians know about it. So we were putting a lot of trust. And of course, I'm not saying that we are frauds, but that trust sometimes might have been misplaced because we couldn't really check and make sure that that was indeed the case. Reproducibility of results means that you take a study and you build a new study, and you try to see, do I get the same result? And reproducibility of inferences means that you have one or more studies, and you ask 200 people in the audience, what do you make of that? People may make different conclusions out of the very same data. So this is the typical recipe of research practices with small data. How many of you work with small data? Okay, so do you recognize that you have small sample sizes, you're struggling to get significant results? How many of you struggle to get non-significant results? Cherry-picking one or best hypotheses, post hoc, p-value of 0.049 is enough? Yes? For how many of you a p-value of 0.049 is not enough? Okay, a few people probably working in genomics or 10 to the minus 8. No registration, no data sharing, and no replication, because why should we waste time to replicate something, especially if it has a high chance or a reasonable chance of not being replicated, and then we spend double the time, and we cannot publish anything in many environments that would not accept negative results. How many of you work with big data? So quite a number, and I think that if we repeat that question a year later, this number will keep growing. I think that until now, most of us had the problem that I don't have enough data, so I'm struggling to get some nice-looking p-value out of them to convince others. Now, one of the main problems in many fields is that we just have too much data. And I have many databases in my computer that I know that almost anything that I will probe in them will get me a statistically significant result. But what does that mean? It means very, very little again. So again, in that environment, there's lots of cherry picking of one or the best looking results. Again, much of that is done post hoc. Many of these big data collections are such that it's very difficult to get an insight about mechanism, about biology, about what's going on here. It's just big data, period. Statistical inference in that case is not necessarily predominantly the typical null hypothesis significance testing of 0.05. It could be idiosyncratic. Each field has its own statistical rules. Some still use p-values, but very often with very lower levels like genomics. Others use Bayesian statistics, others use false discovery rates. There's very little homogeneity across different fields, even though they might be looking at pretty similar questions conceptually in terms of how data are analyzed. Again, usually there's no registration of what were the main hypotheses, and data sharing does happen more often compared to the small world data environment, but much of the time it is not really understood what exactly is being shared. Not only the recipients of the data do not understand what is being shared, very often not even the data generators do not understand what exactly they share. And these databases are just so black box looking that it's very difficult to understand. Empirical studies across different fields where we have performed replications suggest that the replication rate is not very high. And many fields have seen replication as a Me Too type of research that should not be funded, that should be avoided, that no one should waste their time with. But many other fields have run replications for various reasons. One such field, for example, is human genome epidemiology. And the reasons are manifold, but practically in human genome epidemiology, the cost of running experiments decreased about 100 million-fold over the years, with genotyping becoming very cheap. We could create very large consortia of multiple teams with huge sample sizes. Now we have biobanks that even raise the bar even higher. And it was very easy and very natural to start looking in large scale across the genome with rigorous statistical methods and replicating at no cost whatever had been published in the past. So if you compare the 40,000 papers of the quote-unquote candid gene era, when people were discovering one gene at a time for one phenotype at a time, versus what these same gene associations for the candid genes came up in replication in large consortia of GWAS, only 1.2% of these candid gene associations that had been published in the very top creme de la creme journals in the candid gene era really withstood replication. Now, one might say that, John, you were working in human genome epidemiologists and you were doing this because you're stupid and human genome epidemiologists are dumb and everybody else is very smart, and therefore the reproducibility rate would be much higher in other fields that think more carefully and are having better insights about biological plausibility compared to you. That's one explanation. The other explanation is that, yes, I'm probably dumb, but I think my colleagues in human genome epidemiology are very smart and very carefully thinking about methods and also biology. And I don't think that things would be really substantially different in other fields. It doesn't seem that they're different in other fields. So if you go to preclinical research, there's several empirical evaluations, most of them led by industry investigators, but increasingly also done by other teams that have shown that the reproducibility of preclinical results ranges from 0 to 20%. And why did the industry get involved in this? Well, because if they get a lead from an academic paper published in a major journal saying that this is a wonderful new drug target and this can be easily developed into a new treatment, they will spend $500 million, $1 billion, $2 billion to try to develop that. And if it's not a genuinely good lead, they will just waste that money. So they wanted to see how often they can make these things work, and they just couldn't make these things work. Glenn Begley concluded in a famous paper in 2012 in Nature that after being able to reproduce only 6 of the 53 drug targets that had been proposed by top academic teams, he said, the failure to win the war on cancer has been blamed on many factors, but recently a new culprit has emerged. Too many basic scientific discoveries are wrong. This situation has led to what I call reproducibility wars. There's tension behind reproducibility. It's not easy to say that a major finding or even a minor finding does not hold up. There's personal issues at stake, there's ego, there's reputation, there's feeling that one is personally attacked my paper was refuted. In my experience working on empirical research and research, I've never had much trouble saying that 1 million papers are probably wrong, including my own. I've had tons of trouble saying that this specific paper of yours is wrong. And, you know, when it's my paper, then it's a completely different dimension. So people argue a lot about how much of that is a problem in the original paper, how much of that is a problem in the subsequent effort to reproduce, and maybe sometimes how often both the original and the subsequent are okay, but maybe there were some aspects in which they were different that we could not tell. Or maybe both the original and the subsequent were equally wrong, or wrong in different ways, but there's still some fundamental biases that both of them have not been able to tackle. We have such reproducibility wars going on in almost any scientific field that I have come across. And almost on a weekly basis, I hear from colleagues on some field that I had no clue about, that they're still facing some similar situations, and also across very different types of measurement tools, very different types of ways that we try to integrate information and evidence. So here's a partial list that is a bit out of date, but neuroscience, pharmacology, genomics, bioinformatics, stem cell biology, oncology, in vitro testing, chemistry-led discovery, computational biology, pathology, biomarkers, psychology, observational research. This is just within the biomedical field, but there's also huge discussion going on in psychological science and social sciences in general, and economics. Even in the physical sciences, there's a lot of activity at the moment around these issues. Why are we seeing non-reproducible results? There's multiple reasons, but one wants to try to get rid at least of biases. If it's genuine differences, that's okay. We will learn from them and we will try to sort them out. But if it's biases, hopefully we should be able to detect them and then act on them, ideally not after the fact, but preemptively thinking about how to avoid them. About a year and a half ago, we published that paper in PNAS with Dan Fanelli and Rodrigo Costas, where we tried to look at every single meta-analysis that we could uncover across any scientific field. And when there were more than 300, we just took the latest one. We just took the 300 random sample type of range to try to make sense of these data. Now, a meta-analysis is an interesting situation because in that case, there is a perception that multiple studies have been done on the same topic. So at least the meta-analysts thought that these studies could be combined together. They're not necessarily exactly the same, but they're on the similar type of question being asked. And if you see divergence, it could give you a sense whether that divergence is compatible with some type of bias operating on the data. So we looked at 17 different types of biases, and we found most of those in most scientific fields. Not all of them in all scientific fields. So for example, small study effects, which means that you have a pattern where small studies give more prominent results compared to less sizable studies, was very prominent in the social sciences, pretty prominent in the biological, biomedical sciences, not really that prominent in the physical sciences. Why could that be the case? Well, physical sciences, maybe in many of their disciplines, they don't really have small studies. You can think of CERN as the prototype, where you just have a mega study with 30,000 physicists involved in it, and they all join forces to generate whatever papers they generate. Now, you can think of the CERN example being broken down to 30,000 R01s. So instead of having all that money, several $billion or euros or Swiss francs going into a common effort, you decide to give a little bit of a few $1 million to each of 30,000 scientists, and you tell them that within 3 years or 4 years, by the end of the grant, you need to come up with an important discovery. Otherwise, you will not be funded next time. And that would mean you need to find Higgs boson. What would you expect to get? You would get lots of small studies with little bits of observations here and there, and probably you would get more than 30,000 Higgs bosons discovered. Probably some of us would discover 5 Higgs bosons out of them. And I think that this might be one explanation why you see that divergence. But in other areas, even physical sciences have some hints of potential bias. And sometimes they may be even stronger compared to biological sciences and or social sciences. So we have some tools that can indirectly tell us about patterns of bias. This does not decisively and conclusively prove that there's bias in every single study, of course, but it can give us a sense of what might be some high priority areas to try to intervene. In many situations, the availability of very complex data allows us to be very creative about analysis. What that leads to is what I call vibration of effects and the Janus phenomenon. Janus was a Greek-Roman god. He could see in 2 opposite directions, so you can sometimes get opposite results, like in this case, where I'm showing you 1 million different results out of asking the very same question in the very same database. There's 1 million dots in each one of these plots, and they show the hazard ratio on the horizontal axis and the minus log 10 p-value on the vertical axis for questions like, in the far right panels, whether vitamin E affects the risk of death. The data come from the National Household Survey in the US. It's one of the best surveys, probably the best survey in the US in terms of representativeness of the population. And how do I get 1 million different results? Simply, since this is death risk, there's 20 other things that can affect death risk. So depending on whether I adjust or not adjust for each one of them, I can get 2 raised to the 20th power options of running that model. Unless I have pre-specified which one of these analyses I want to run, I will get 2 to the 20th options, which is 1 million options roughly. And 70% of those would suggest that vitamin E decreased the risk of death. 30% of those would suggest that vitamin E increased the risk of death. So complexity and lack of pre-specification for hypothesis validating research as opposed to hypothesis exploration, which is obviously open to any type of exploration that can be done, can lead to some weird circumstances. Probably this is how you get this type of research result being presented. This is not a joke. This is one of the 20 highest impact papers published last year in terms of altmetric scores. It had an altmetric score of something like 4,000 or something, or maybe more. And basically, it was an observational study concluding that with 3 cups of coffee per day, you can decrease your death risk by 17%. So I was a bit late this morning. I missed a cup of coffee, and this means that I'm lagging 6% behind in my risk of death. And it's not just nutrition. You can see the same kind of situation in almost any field that has a high dimensionality of potential analysis. This is some examples from psychiatry. If you look at the bottom right panel, it's about whether having a hearing impairment affects the chances of becoming psychotic. And depending on how you analyze the data, you may conclude that not being able to hear makes you mad, or there's hardly really any effect about that. Some people argue that we need less science. You know, we just have too much noise, too much junk, too many scientists, too many journals. Just cut back on science. Just fund only the very, very best. And same for journals. You know, just keep a few journals and get rid of these 100,000 periodicals that are circulating around. I don't really believe that. I don't think that there's a way that you can just eliminate or shrink science and make it better just by shrinking it. I think that improvement by shrinking leads to death. And even the very best journals can have reproducibility problems. A couple of weeks ago, a wonderful team of colleagues published that paper in Nature Human Behavior, where they showed that for 21 high-profile papers published in Nature and Science, when they tried very thoroughly to reproduce them, they could reproduce about 60% of them, and on average, the effect size seen in the reproducibility experiments was 50% of the original. So you can take an effect size and cut it in half, but the problem is that you don't know exactly which one to cut in half. Experts might be able to tell you and navigate through that mess. For example, in prediction markets, they have some insider insight of what are the experiments, what are the studies that may have a higher chance of being reproducible. But even experts need some insider knowledge and they need some time. For example, in the prediction markets for that investigation, these studies had been out there for a few years. It was not that they just came out and the expert read it and that same evening told you that, oh, that's going to be non-reproducible or it is going to reproduce. And again, even Nature, Science, and PNAS, they still have the very same patterns that we see in other journals. In some aspects, maybe they even have more of some of these weird patterns. For example, if you look at tables and figures of papers published in Nature, Science, and PNAS, 98% of the p-values shown in these display items are statistically significant. And you would expect that a table or a figure is one opportunity to give a little bit of an unselected view of results. I mean, you can highlight significant results in the text, but why should everything be statistically significant in a table and a figure? I mean, that blows my mind. And even when there's adjustment for multiplicity of comparisons, again, 87% of these results are statistically significant. So we have some issues, we have some challenges, we have some opportunities, and we also have solutions to these problems. And some of these solutions are pretty well known. Some of them are easily recognized and easy to apply. For example, experimenter bias has been known since the 1950s, and we have ways to deal with that. For example, blinding assessors who read the outcomes of experiments. However, they're not necessarily applied. Somehow we have a disconnect between knowing what needs to be done and doing what needs to be done. Other solutions are very speculative. You have weird people like me saying, do this, and you should not take me very seriously. You should think, what is the evidence for that? Is there proof that this is going to work, that this is going to make things better, that this will enhance the reproducibility, the credibility of the results? So we need also empirical evidence on some of the solutions that are being proposed. These solutions may act at different stages in the process of doing research. And the question is, where do we need to intervene? Should we intervene early on or late? In principle, it makes sense that if we can intervene early on in the chain of thinking about the research agenda and designing studies, it would be better compared to, let's say, design a horrible study or perform a horrible study or have a miserable analysis and then someone try to salvage the whole enterprise at the end of the day. However, acting early does not mean that we can solve all the problems, because even if you design a study very carefully, obviously it can easily run apart while it is being run, while it is being analyzed, or while it is being reported. I've seen many papers that I just go through them and I say, amazing, these people are wonderful. And then I look at how they run the study. That's fantastic. And then how they analyze the results. This is perfect. And then you see just the conclusion and it's completely off. So I think that finding ways to intervene at the right level and probably across all levels would be best. These are 12 families of research practices that may help increase the proportion of, let's say, true or quote-unquote true research findings. Large-scale collaborative research, adoption of replication culture, replication of studies, protocols, analysis codes, data sets, raw data, and results, sharing of data, protocols, materials, software, and other tools, reproducibility checks, containment of conflicted sponsors, authors, and editors, more appropriate statistical methods, standardization of definitions and analysis, more stringent thresholds for claiming discoveries or successes, improvement of study design standards, improvements in peer review, reporting, and dissemination of research, and better training of the scientific workforce in methods and in statistical literacy. I will run through a few of them. Here is one example of collaborative research. Human genome epidemiology had that transformation that allowed it to get from a field that had 1% chance of being correct to 99% chance of being correct when a new gene-disease association is being proposed. It took collaboration, it took merging of dozens and hundreds of teams, sharing their data and using common analysis with raw data being shared among the teams, with multiple analysts looking with very rigorous statistical methods and comparing notes on how data are being analyzed. When we did that, at some point, this is a Manhattan plot from a GWAS of smoking behavior, and even though we thought that we had discovered 359 genes before we did that, when we run these analyses, only one of them survived, and 3 new ones emerged. So one might say, well, this is disappointing. You thought that you knew 359 gene disease associations, and now you know only 4. But that was a good start, because following that path, now we have, again, hundreds of gene disease associations with very rigorous support, with high transparency, with everything being shared. And I think that most, if not all of them, are likely to be genuine. Registration is also a very useful idea. And it has been used extensively in some fields. It's used far less in others, but probably there could be far more uptake. Not everything needs to be registered. Let me just be clear about that. There's a lot of research that is entirely exploratory, and there's no way that you can register research that is entirely exploratory. It would be fake. You know, it would actually be damaging to have a blue sky science exploration type of work presented as if it was pre-registered and pre-thought and pre-specified, because that's not really what happened. Exploratory research needs to be described as such. It's extremely valuable. It is one of the major ways that we can have leads to make major discoveries, but at the end of the day, it should be presented as exactly what it is. That was an exploration, and can you please now validate it? The validation phase can be registered, and there's a lot of research that can be registered. There's also different levels of registration. One level of registration would be registering data sets. If you have data sets that are used for exploration analysis, so kind of hypothesis generating tools, maybe you cannot fully register a specific protocol because the data are there and anyone could analyze them in any different way. I mean, the data has been collected, it's sitting in a computer. Maybe what can be done is just recording the availability of these data sets. So I can register the data sets so that people would know that I have these data sets available in my computer, and they contain so many variables on so many different things and so many observations. And tonight I can press a button and launch 5 trillion p-values against humanity, if I want to. It's a little bit like telling you about the size of a nuclear arsenal and its capability. It doesn't mean that I use the nuclear arsenal, but it is there. Level 2 would be registration of a protocol, and that goes much further. It means that there is a protocol. Someone has thought about a specific sequence of design, of contact, and on how to run the study. And in many fields, we start seeing availability of protocols, and in some cases it's even becoming routine, like in many top medical journals that ask for protocols to become available, even timestamp protocols, so that someone could see that this is exactly what was promised to do. Registration of an analysis plan goes an extra step, because I have seen many protocols that are 250 pages long, but you look for the analysis plan and there's no analysis plan. There's a lot of biology and mechanism and thinking and importance and innovation but there's no analysis plan. Some senior statisticians say that in many cases you cannot come up with an analysis plan until you have the data. There's some partial truth to that. Indeed, sometimes you may be surprised. Things may happen that you had not anticipated. However, you can really put a lot of thought ahead of time, and it's time well spent, about what exactly is going to happen, and therefore what is the most likely analysis plan that I have carefully thought about. If there are deviations, then these can be recorded and explained why they had to happen. Level 4, you have both the analysis plan and the raw data. And this is even better because now you don't have to just put faith in your colleagues, but you can have the raw data, and if you want to spend a day, a week, a month, a year to reanalyze them, one can really do it. And level 5 would be live streaming, open to the entire community, like in the case when NASA published a paper in Science claiming that there's alien life bacteria that use arsenic instead of phosphorus for their DNA backbone. A professor at UBC had that open live streaming, posting the experiments that she would run online, getting feedback from the entire scientific community, revising the plan, running the experiments, showing them to everyone, getting more feedback, revising, and running the second line and so forth until it was proven that these alien life bacteria actually did not use arsenic, because that would not really be possible. This is a registered report from a reproducibility check. There's more than 100 journals that use registered reports nowadays, and I think it's an interesting idea. What it means is that a paper is submitted for peer review and is accepted before the study has been run. The study has been designed, and you can even put the tables and the figures in place and say that this is how the tables and the figures will look like once I have the results to populate them, but please judge the quality of the intention. So the paper is provisionally accepted, then here come the data, they populate the figures in the tables, and the paper then is reappraised briefly just to make sure that there was no major deviation, or if there was a deviation, it was pretty much explained for some reason and then published. Is that something that we can do for every type of research? Again, you cannot do that for exploration research. Lots of blue sky science will not fall into that remit. But for things like reproducibility efforts, that's ideal. And for lots of hypothesis testing, validation research, again, it may be a good principle to have this maximal transparency and kind of early review of whether the paper is really worth it, regardless of what the results would be, so that there would be no pressure to the investigators to get a particular type of result. Data sharing has started happening. About 10 years ago, a bit less, 8 years ago, we run an evaluation of the top 50 journals across science in terms of impact factor. About half of them were biomedical, the others belonged to other fields, and we asked how many of them have policies in place for data sharing and encouraging data sharing. Green color means good news. They share data, or at least they have policies to share data, to share protocols, share materials, to share whatever was of interest to the field. However, very, very few of these journals actually had papers that did that. So it was encouraged, it was nice, but it was not happening. And I'm not saying that to blame anyone, because we all recognize that sharing is not easy. You need to have a framework in place. You cannot do it alone. You need to have infrastructure. You need to have a credit system. You have to have some reassurance that these shared data are not going to be misused, that both the generators of data and the users of data will get some benefit out of that. There need to be some rules in place, and unless these rules are in place, it's not going to happen. These rules start getting in place in many fields, and I think that we see far more data sharing currently. A few years ago, we did a survey of the entire PubMed with a random sample from papers of 2000 to 2014 publication years. We saw very little data sharing. We have a paper coming up that is looking at the period 2015 to 2017, and the rate has gone up to 20%. So if you take 5 papers out of biomedicine, one of them shares raw data. I think one might say, well, this is less than half full. I would say, going from 0% to 20% for the average paper, and obviously in many environments that 20% would be 50%, 70%, or even 100%, I think this is clearly moving in the right direction. Reproducibility of methods. There's also a lot of things that can happen on that frontier, and a lot is happening. A couple of years ago, Victoria Stodden led that effort, trying to put together some recommendations and some levels of reproducibility for computational methods. And I recognize that not everything can happen overnight. So the lower level is something like, if you see a link saying the script is here, or the software is here, or the data is here, just click on it. Make sure that you don't get an error sign. And that's not uncommon. So that's very easy to do, very easy to check. There's higher levels, and it can go all the way to reanalyzing everything that is being available in a scientific publication. Keith Baggerly had been doing that for years, trying to prove that a number of microarray gene expression experiments were wrong. Nobody was paying attention to what he was saying until it was realized that the PI had claimed that he was a Rhodes Scholar, and then people started, but he was not, and people started looking more closely, and they realized that indeed everything was wrong. But I think that we will be able to see more of reproducibility and what Keith has called forensic bioinformatics or forensic analytics in the future. Better statistics and methods can also make our life easier and more credible. It's been demonstrated repeatedly that the quality and the rigor of statistical methods that is being used across most scientific fields is not really very high. There's clearly plenty of room of improvement. There's clearly plenty of room of improving scientific literacy and numeracy in terms of statistics and methods. Sometimes there's easy choices that are being neglected. For example, I mentioned experimenter bias at the beginning of my talk. Even though we know that it's a major thing and it's very easy to tackle in animal experiments just by having blinding of the investigators who read the outcomes of the animals' experiments, this is not happening. It's only happening about 5 to 10% of the time. Or randomization, so easy to do with animals, but again, it's not happening more than 30% of the time. Should we change our statistical methods? There's a lot of debate about that. Several months ago, we had that paper published, and we have 72 authors where we said that one easy way to cut a large section of the noise is to move the threshold of statistical significance from 0.05 to 0.005, so add an extra 0. Is that a good idea? Practically, it's a temporizing measure. It's just getting rid of about 30 to 40% of the scientific literature, moving it from statistically significant to just suggestive. Some real interesting, useful discoveries will move into that suggestive zone, and they're actually important, real, true, and impactful, but the vast majority that will be moved would be noise. Obviously, that's not the end of the story. There's some more fundamental questions. Are null hypothesis significance testing methods that almost all of us use the best thing to use for things like developing a prognostic score, assessing a diagnostic test, evaluating a therapy, mining electronic health records, mining big data? No. They're suboptimal for all of these applications. In fact, about 80% of the millions of papers that use null hypothesis significance testing could have used some other inferential tool that would be much, much more suitable. However, it takes time to train investigators in methods. It takes time to retrain investigators in methods. And who is going to do that? I think that institutions need to do that. We need what I call CME, which is not continuous medical education, but continuous methodological education. We are all trained in the little bits of fancy tips of new technologies, but less trained on methods and how to optimally apply them. And of course, if more people are trained in methods, then we can talk about other inferential tools that may be more suitable to apply on a vast scale across different fields. In many cases, our research practices are so complex and so intermingled with other things that we do and what multiple stakeholders do that it's very difficult to get experimental evidence about them. It's not easy to randomize 500 national institutes of health, 250 of them to have one type of research practice, and another 250 NIHs to have a different type of research practice. So we may need to resort to some modeling. We need to think about other tools like game theory or modeling and simulations of scientific environments to try to understand what would happen under different circumstances, under different structures. And this is one such example of one model that I built with David Grimes. We used 11 equations to describe science. So it's a scientific universe that is being built with 11 equations. And we played a game. Basically, we said, There's 3 different types of scientists. There's diligent scientists, which are the large majority. There's some careless scientists, which are a minority. And there's about 1% who are frauds. They're not more than that. Fraud is very, very uncommon. And we run through different reward games. So one option was to reward everyone the same. No matter what is the quality of my research, I will just get the same benefit if I get a significant result. If I'm diligent, sloppy, or a fraud, it's just the same. If you do that and you run through the simulations, you realize that within a few years, the careless and the unethical cohort will take over. And the reason is easy. You don't have to have 11 equations to prove that. If I can get the same credit by doing less work, in less time, with less resources, actually even better by doing no work, just coming up with 1 million patients that do not even exist, I will get there faster. So we need to find the right rewards and the right, perhaps, penalties in some cases, and use a reward and penalty system in a way that would promote better science. And this is what many meta-research investigators are trying to do, trying to understand how best to perform research, how best to communicate research, how best to verify research, how best to evaluate research, eventually how best reward research. The reward system is at the center of whatever we do. We need to incentivize the best practices, and this is what my Meta Research Innovation Center at Stanford is trying to do. So what do we want to reward? We can reward productivity. I love productivity. I love writing papers. I write publishing nonsense. I'm addicted to that. I have nothing against productivity, but we need to find ways to reward also other dimensions. We need to reward quality, we need to reward reproducibility, we need to reward sharing, and we need to reward eventually translational impact for people who do applied research. And I think that this is where we need to focus more, and I'm sure that there will be brilliant ideas by the panelists this day. We need eventually both evolution and revolution. And a couple of years ago, along with several colleagues, some of them are in the panels today, we published that paper, which is a manifesto for reproducible research, and thinking about the different stages of research that one could intervene and improve the outcomes, the credibility, the reproducibility, and the usefulness of research. There's multiple stakeholders involved in that process, and not any single one of them can do everything. There's journals, there's publishers, there's funding agencies, there's professional societies, there's sometimes the general public can do a lot. I mean, currently we live in an environment where there's a lot of anti-science angst surrounding us, and I think that we can work with the general public to make them understand how difficult science is, how noble it is, and how we can, and we want their help to get it better. These different stakeholders have different priorities. Many of us love publishing papers. Many of us want to get funded, and this is, of course, understandable. Many want to see things translated, and of course, this makes sense. And many want to make profit, and there's nothing wrong with that. We need to find ways to integrate all of these stakeholders to work towards a common goal, a common direction of getting the best possible science in a most efficient way. So I will close with these conclusions. The reproducibility and usefulness of many disciplines in biomedical research and beyond has substantial room for improvement. There are many possible interventions that may improve the research practices and enhance the credibility of the scientific investigation. Fostering excellence requires proper incentives that align with this goal, and much of what we incentivize currently may need to be revisited, hopefully with evidence. Closing with some special thanks to a number of my colleagues who have contributed to the empirical data that I showed you today, and with many thanks to all of you for listening. Thank you.
Is this on? Okay, good. Thanks, John. Maybe we could, if there are questions, a couple of people could line up, and at the same time, maybe I'd invite the panel, the next panel, to come to the podium.
And I'll get into trouble. I am helping to put together a database for pediatric research We have about 1 million patients, and of course, many different factors such as diagnoses, treatments, what have you. And as you've pointed out, there's a lot of potential for abuse because of all the factors can be looked at. What advice would you give us in setting up this database and making it available? We're already planning to register analysis plans and have them approved by committee.
So if you're doing this for the first time in the field and there's no precedent, it's both a blessing and a curse because there's no established rule. You need to set up the rules and maybe one can use some rules from other fields that may have done that, but there's always some peculiarities about each field, what exactly is being measured, how it's measured, what is the reliability of different types of measurements within that database. Some key principles, and obviously this can be a whole volume of instructions of navigation, is to make sure that this is going to be in a usable format, that it's going to be understandable, that the potential to misuse, at least unintentionally, goes down. Because I think that lots of databases are just thrown out, and then people start producing some very weird results and they don't recognize that that was not really age, but it was uptake of cholesterol instead of what was the age of the patient. So I think transparency, consistency, careful cleaning, also some interface with the investigators that there can be queries about how to use a database and what it means. And I think that can go a long way. I think that Brian Nosek will be speaking later today, and he has created a wonderful framework for transparency of making things available, and also in ways that they do not perish, because this is another major issue, that sometimes we place somewhere a database or a protocol or some other tool, and a couple of weeks later or a couple of months later or a couple of years later it disappears. So it needs to be in a format that will not perish, and even if the supporting structure perishes and the investigators, unfortunately, we all pass away at some point, it will still be there for people to use.
Thank you very much.
Steve Jaffe from Penn. Thanks for a great talk. One of the things on one of your slides that caught my eye was observational research refuted by randomized controlled trials. And I'm an oncologist, and we have a great deal of difficulty in oncology and other fields in convincing people to do randomized trials, partly because of ethical concerns and concerns about withholding therapy or potentially effective therapy from patients. So given the importance of doing randomized trials to actually getting valid results, how do you tell a story? How do you sell randomized trials? How do you make the case for them to the public, to physicians, to others who might be resistant against doing them, given what you've showed?
This is an interesting question, and it's not easy. To be honest, for many questions, it's not possible to have randomized trials. Maybe the majority of questions cannot be answered with randomized trials. I love Marcia's comment that you cannot randomize people to an earthquake or a volcano eruption or not. However, you can do randomized trials on lots of important questions in many fields, and they're actually easier and more suitable than many people think. Actually, there's lots of randomized trials that are happening beyond the core science visibility, like A/B trials that companies run, like Google, all the time. You know, they run hundreds and thousands of them, and this is how they become billionaires. So I think that you need to have a consistent message that for some questions that are largely unknown, that we have equipoise, that we don't really know what to do, that it is ethical and we're not going to harm people intentionally. If we don't know, we need to randomize. Because otherwise it's going to be very, very difficult to reach conclusions. We could have some leads, we could have some tentative knowledge from observational data. I don't want to discard that possibility, but when I want to choose the best treatment, I really want randomized trials, ideally. And the counter-arguments that they're expensive, yes, if you want them to be expensive, you can make them actually much, much cheaper. We have ways to make them 100 times cheaper. That they take a long time, yes, sometimes they do, but sometimes you can get early responses and early answers. And even those that are long-term are essential to be long-term because you're interested in things like death. So if you care about how you improve your biochemical markers, yes, maybe you can find out within a day. But if you care about whether you're going to live longer, you need to wait and see if people die or survive. There's lots of arguments, and there's a lot of tension, obviously, and a lot of pushback.
Thank you.
Okay, thank you. I think that we'll be able to return to some of these issues as the panels are going on. They'll certainly come up, and those of you who had additional questions you wanted to ask will be able to participate in the subsequent session. So thank you, John. Thank you very much.